It is time to learn box plots. Along with dot plots and histograms, a box plot should be something that a statistician has in their tool belt. They're used to describe and compare distributions. They can be used for one, or putting them side by side is going to be really helpful, so that we will compare distributions. And they also show outliers. So we'll find a mathematical formula that determines if something is an outlier or not. Here is a standard box plot, also called a box and whisker plot, because there is a box here, and then sometimes there might be a whisker, these extensions going off left and right, and that is a standard box plot. Those vertical bars represent things. The very middle one, let's start in there. That is the median, the very middle number. And then as you extend to the left or the right, the next one to the left, that is quartile 1, also called Q1, the 25th percentile. 25, that means 25% of the data is to the left of that number. Quartile 3 is the right side of the box, or the right endpoint. And then the whiskers represent the minimum and the maximum, meaning the lowest number and the highest number. Min and max. These numbers here, min, Q1, median, Q3, and max, are called the 5-number summary. And when you perform a calculation of one variable statistics on your calculator, those are the numbers that will come up. So you will make a box plot by hand, and then we'll also show you how it happens on a calculator. But those numbers, minimum, Q1, median, Q3, and max, are called the 5-number summary. So these quartiles that are right in the middle here, and the median is really like quartile 2. That means it's the very middle number. It divides absolutely from left to right, the middle 50%. The box is there because that is called what's called the interquartile range, the IQR. That's the middle 50% of the data. As you get used to different box plots, you'll see that this median could slide. I mean, it could have a skew in some way, so the box plot will not be symmetric. So, okay, let's put it to let's do a practice here. Let's pretend like Miss Howe and I, who live in different areas of Seattle, but who also just have first graders who are really excited about Halloween. Let's say that we took some data in Halloween and we randomly found first graders from a certain point of time, like 7 to 7:30, and we sampled them and said, hey, excuse me, do you mind if we just look in your bag, or can you tell us how many pieces of candy you have at that certain moment? Because you know how kids are. They want to compare, like, hey, where's the best place to get candy? So let's pretend that Miss Howe and I got these data. Peabody, who lives in Ballard, Howe and Lincoln, who are in Bryant. Those are our numbers. Let's do a box plot for those. Let's start with the Peabody Ballard one. Here are the steps to create a box plot. Number 1 is to put the numbers in order. In your calculator, if you have them, you could do a data sort, and that will take care of it. Or otherwise, it doesn't take long if you take them. I'm going to copy them here, and then I'm going to expand, because we're going to be working with that list. Number 1 step is put the numbers in order. Number 2 is to find the median and quartile 1 and quartile 3. Find median, Q1, and Q3. The way you do that is you work inside out. It looks like Peabody's has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 12 sets of data. So this is where I'd put my pen down and kind of work in to see what is the very middle number. It actually is not a number. It comes in between 17 or 18. That's okay. You find the mean of those, the very middle. So the median is actually not a data set in here, but it is 17.5. If there's an even number, you'll have to do some quick calculations. And now I work to the left and to the right. I take these, let's go to the right, I take this set of numbers here, and I find really the median of them. So between 18, 19, 19, 20, 20, and 22, my quartile 3 is, in between 19 and 20, 19.5. And it looks like 22 is my maximum so far. Working to the left, I take those 6 data points, I still use them all, and it looks like the median in between those 6 is going to be 12. That is quartile 1. And my min is going to be 12. Okay, all right, so step 3, you could, let's put this on the graph. Let's put the box on the graph. As I'm looking ahead, I see that we're going to stack these bar graphs. We're going to do both Peabody and Howe's, and it looks like the min for both of them is 10 and the max is 25, so I need to increment my graph so that it will go to both of them. Let's see, I'm going to put it, how about I put it right here? And I'll put Peabody up here, leaving some space for the Howe box plot. And I'm just going to start counting. Probably I'll start at 5 and then go up to 25. So 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 23, there's 25. And my box, the Peabody box, it looks like it is from 12 to 19.5 with a median at 7.5. 12 to 19.5 with a median of 17.5. Something like there. I have refrained from doing the whiskers yet because we need to test for outliers. This is where there's a formula that most math statistics books use, and that's the one we'll adhere to. So step 4 is find any outliers. An observation is an outlier if it is more than the following. If it is more than 1.5 times the IQR above quartile 3, or if it's 1.5 times the interquartile range below quartile 1. So you take your interquartile range, which I haven't told you yet, it's quartile 3 minus quartile 1, and then you do some calculations. Okay, let's go back to the interquartile range. That is this thing right here. That was from 19.5 down to 12, and the interquartile range, let's see, can I give you some space here? IQR is quartile 3 minus quartile 1. It is just a measurement of how much of a span the middle 50% occupies. And so that is used to determine if something is an outlier. So let's do the calculation for p-bodies. If it is, let's see, let me change color here. How about let's check red. I'm going to take Q3 plus 1.5 times the interquartile range. That means I'm going to take Q3 is 19.5 plus 1.5 times 19.5 minus 12 is 7.5. I'm doing a box plot with your candy data, actually. Double check my math there, and that is...
Daddy, who are you telling?
These are all my students. Me and Miss House students.
Class on the weekend?
It's not class, I'm making a video for them.
This is real.
And that becomes 30.75. That's like the fence post. If you double check to see, hey, are there any data points that are above that number, on it or above it? If there are, those qualify as outliers. 30.75 compared to the max of 22, that is not in, it does not go past 30.75, so 22 is going to be my max. And I can make my whisker right there. Back to the test for the left outlier. If it's 1.5 times the IQR below quartile 1, that means I'm going to take Q1 minus 1.5 times my interquartile range. And that means my quartile 1 is 12 minus 1.5 times my interquartile range, 7.5. Double check math here. It looks to be pretty low, 0.75. The lowest person had 12 candies. That is not even close to the 0.75. So I put a none, meaning no outliers, and I can complete my whisker, my left whisker here at min at 12. Oh, it looks like, wow, there's so many data points at 12, so many instances that I don't even have a whisker. That means that the 12 is not only the minimum, but Q1. That sometimes happens, that it's so dense in here that it does not show up as a left whisker. Okay, what we're going to do now is I'm going to pause you, or actually I'm going to stop the video and see if you can't go ahead and take the Howe-Bryant data and make a box plot from them. I'll take it from the beginning, and then what you're going to do is, once you identify the box plot pieces, you'll put them down in the Howe area, and then we'll make some comparisons, because that's the best thing about box plots is you can stack them and compare their distributions. Okay, so now you are taking the Howe-Bryant data and making a box plot. See you in episode 2.